పేపర్ 1 మాకు పెట్టలేదు మరి. మీ గ్రూప్లో పెట్టారా పేపర్ 1? పేపర్ 2 పెట్టినట్టున్నారు
సార్. మళ్ళీ ఫార్వర్డ్ చేయాలా సార్?
పంపించలేదే. మీ గ్రూప్లో పంపించారా పేపర్ 2 పేపర్ 1?
పంపించారు సార్. మళ్ళీ ఫార్వర్డ్ చేసాను ఇప్పుడు వేదవ్యాస్ గ్రూప్లో.
ఓకే 8th one. ఓకే. Given a plus b by c square into d minus x is equal to y, then dimensions of a and b must be same. A and b dimensions must be same. That is incorrect, no? Dimensionally a and b by c square are added, no? A is equal to b by c square అవ్వాలి కదా.
Yes sir.
Okay, and d and x have same dimensions. And later you can split that. Later you can multiply that, and again accordingly we can calculate. Dimensions of d and x must be same. This is correct statement. So a and b may not, they don't have same dimensions. A is equal to b by c square. Okay. And by multiplying this, we get AD minus AX plus BD by C square minus BX by C square is equal to Y, no? So dimensionally AD is equal to Y, AX is equal to Y. Like that we can write, no?
Yes sir.
So AD dimension formula must be equal to Y. These two correct. Next one, 11th. A man applies a force F on the spring block system as shown towards the right when the block is at rest and spring is relaxed. Man applies a force and spring constant of the spring is K. Force right, the block is at rest when the spring is relaxed. If F is constant, then time period of that block is 2 pi root over m by K and amplitude is F by K. When the block passes through the equilibrium position, the energy stored in the spring and kinetic energy of the block respectively are F square by 2K and F square by 2K. The block does not oscillate. Here F is constant. F is constant means at every instant, what the work done by that applied force plus work done by that spring force is equal to change in kinetic energy of the block, no? Suppose when it reaches to the maximum displacement xm, work done by that applied force should be F into xm minus half K into xm square is equal to kinetic energy initially at rest, and finally on reaching this position also it is at rest. We can assume it is extreme position or maximum elongation of the spring is xm. So which upon simplification x max is equal to 2F by K. So that is the maximum amplitude of oscillation. Amplitude of oscillation we get 2F by K. Now, for small displacement, here the block is constant force is applied. Constant force is applied. Here, one more thing we need to calculate here. Energy, kinetic energy of that block respectively. When the block passes through the equilibrium position, means F is equal to Kx. When F is equal to Kx, where net force is 0. Equilibrium means? In equilibrium, net force is 0. Where we can assume F is equal to Kx, then apply the again work energy theorem. And what is the work done by that applied force? Fx, energy stored in the spring is half Kx square kinetic energy, change in kinetic energy, we can say half mv square. So x is equal to f by k, we write half k into f square by k square. That is initially block is at rest, and while reaching the main position, this is the equilibrium position. In between extreme and rest position, we have a mean position. Therefore, kinetic energy acquired by the block, we get it as 1k get cancelled here, delta k, we get f square by k minus f square by 2k, we get f square by 2k. Half kx square also we get f square by 2k. Energy stored in the spring, we get f square by 2k, and kinetic energy acquired by the block is also half kx square. Then what are the values they give? Not on. Energy we get f square by 2k, and kinetic energy we get f square by 2k. Sorry, here x max is equal to amplitude they want to calculate now. So in between these two, we have intermediate position. That is the mean position now, in between. So this is the XM is a maximum elongation from the rest position. Initially it is at rest at the left extreme, this one. This is right extreme, and this is the mean position. So here XM is equal to amplitude of oscillation mean from mean position to left extreme A, and the mean position to right extreme, it should be A. Therefore, XM is equal to 2A. Therefore, amplitude of oscillation, maximum elongation of the spring is 2F by K. So amplitude of oscillation is F by K. Amplitude of oscillation is F by K. Therefore, and the time period of oscillation is F is equal to minus Kx. So in equilibrium, restoring force is provided by that spring force. So therefore, and time period of oscillation of that spring block system, we get it as 2 pi root over m by k for small oscillations. So if that means from the equilibrium position, so from the equilibrium position, if the spring is pulled aside and released, so it executes oscillations about the mean position. Therefore, restoring force is equal to minus kx. From that, we get time period of oscillation, we get 2 pi root over m by k. So amplitude of oscillation, we get f by k. And in equilibrium, net force is 0. Therefore, F is equal to kx, applied force is equal to kx. And from work energy theorem, work done by that applied force plus work done by the spring force is equal to change in kinetic energy. So when the block is moved from left extreme, means initially it is at rest, from that position to mean position by a distance x, then kinetic energy acquired by the block. We get it as F square by 2k. Okay, Natanj. And the remaining. So units and measurements, easy questions only now.
Yes, sir.
Physical pendulum, they give numericals, amplitude of simple harmonic motion. What is the resultant amplitude? Superposition of two SHMs we discussed in the last class.
Yes, Regis.
Phase difference we can calculate resultant amplitude root over A1 square plus A2 square plus 2A1 A2 cos theta or cos phi. The calculation part will be there in terms of significant figures in 17th. Okay. And remaining, okay now? In paper 2?
సార్ పేపర్ 2 క్వశ్చన్ నెంబర్ 7 కూడా చెప్పండి సార్.
Question number 7. 7 and 9. Huh? Question number 7. In damped simple harmonic motion is given by x is equal to a naught into
ఓన్లీ డి ఆప్షన్ డౌట్ ఉంది సార్.
e power minus bt by 2m into sine of omega t plus alpha. Exponential and trigonometric functions are dimensionless. So choose the correct options. Dimensions of m by b is same as t annadu. So here exponential functions are dimensionless now.
Yes, sir.
And this is also dimensionless. Okay, sine of omega t plus alpha. These are the dimensionless. So bt by 2m is equal to 1. Therefore t is equal to 2m by b. Therefore m by b, dimensions of m by b same that of t, because 2 is a number, there is no unit. So first one is correct. Dimensions of a naught into omega. A naught into omega. What are the omega t plus alpha? What is meant by alpha here? They will mention or not.
దే డిడ్ంట్ గివ్ ఎనీథింగ్ సార్.
Yeah. So omega t plus alpha is 1. So alpha equal to 1 kada dimensionally. Principle of homogeneity. Alpha equal to 1 means dimensionless.
Yes,
And
sir.
omega t is equal to 1. Therefore omega is equal to 1 by t now.
Yes, sir.
Yes, sir.
Now these two terms dimensional is x equal to a naught kada. X equal to
Yes.
a naught. Therefore dimensions of a naught into omega annadu. A naught into omega, how much we get? A naught means L. Omega means T inverse. A naught into omega we get LT power minus 1 kada. Kaushal.
ఎస్ సార్. సార్ ఇది ఆప్షన్ డి లో యూనిట్ లెస్ కూడా అన్నాడు సార్, ఒకసారి చెప్పరా అది?
యూనిట్లెస్ అంటే జనరల్ గా ఇది నెంబర్ కదా, ఒమేగా టీ ప్లస్ ఆల్ఫా. ఇప్పుడు ఒమేగా టీ ప్లస్ ఆల్ఫా అనేది ఎనీ ప్యూర్ నెంబర్ కి ఈక్వల్ చేస్తాం, సమ్ కాన్స్టెంట్. ఓకే, బట్ ద డైమెన్షన్లెస్ క్వాంటిటీ ఇట్ ఈస్, but it is equal to 1 means any pure number we have to equate dimensionless. So that's why it has unitless and as well as dimensionless.
సార్ నేను డి ఆప్షన్ పెడితే నాకు మా నెగిటివ్ మార్క్స్ ఇచ్చారు సార్, తప్ప అన్నారు సార్.
Unitless and dimensionless అంటే ఇక్కడ ఆర్గ్యుమెంట్ కదా, సారీ ఆర్గ్యుమెంట్ లో ఉంది కదా. అది ఆర్గ్యుమెంట్ అంటే ఏంటో ఉండాలి, యాంగిల్ రేడియన్స్ లో ఉండాలి కదా యూనిట్.
రేడియన్స్ లో ఉంది కాబట్టి అలా
ఆర్గ్యుమెంట్ లో ఉంది కాబట్టి రేడియన్స్ లో ఉండాలి కదా. ఫిజిక్స్ వి రైట్ ఇట్ జనరల్లీ ఒమేగా టీ ప్లస్ ఆల్ఫా, యూనిట్ ఫర్ దట్ ఒమేగా ఏముండాలి, రేడియన్ కదా. సో ఒమేగా టీ యూనిట్ రేడియన్ వస్తుంది, ఆల్ఫా యూనిట్ కూడా రేడియన్ రావాలి.
ఓకే.
And what about 9th one? In the figure shown, a vessel is filled with a liquid whose density varies with the height from the bottom, as rho is equal to rho naught into 4 minus 3h by h naught, where rho naught is constant, h naught is the height of the liquid in container. A solid block of small dimensions of density of solid 5 rho naught by 2, and mass m is released from the bottom of the tank, then the block will execute. Here the density of the liquid varies. The depth h is equal to h naught. At h is equal to h naught, what is the density of the liquid? At h is equal to h naught, density of the liquid is 4 minus 3, 1 rho naught now. 4 minus 3, it should be rho naught. Therefore, here initially the solid is at the depth h naught. When h is equal to 0, we get 4 rho naught. H is equal to 0, we get 4 rho naught. Then the density of that liquid is less than the density of the solid. 5/2 అంటే ఎంత వస్తుందో 2.5 కదా. It is 2.5 and on the surface ఎంత ఉండాలి density, liquid of density. When H is equal to 0 in this region, the density of the liquid at the top we get it as 4 rho naught. So initially at the top layer, the density of the liquid is more, the density of the solid is less. So when it is kept under the water, so that where the block means when the density of the solid and that block density are equal, then solid will be in equilibrium, no?
Yes, sir.
So solid is in equilibrium. Solid in equilibrium means equilibrium position. About the equilibrium position, actually, if it exclude SHM, about that equilibrium position, it exclude SHM. That equilibrium position we need to determine. What are the forces acting on the block actually inside the liquid? Buoyancy acting upward and
Upward,
mg acting downward. Mg acting downward. So in equilibrium of block, weight of the block should be balanced by buoyancy force. Equilibrium of that block, mg should be balanced by mg. So mass of the block can be written as volume into density. Volume into density. So here given mass of the block is m only, and the buoyancy force. Buoyancy force. A solid block of small dimensions of density 5 rho naught by 2 and mass m. Small dimensions. Volume is equal to mass by density. So here mg is equal to buoyancy should be volume of that solid. Volume of the solid into density of the liquid into g. So volume again we read it as mass by density of the solid. Therefore mm get cancelled, g get cancelled. Therefore in equilibrium density of the solid is equal to density of the liquid. So density of the solid at depth h we get it as density of the solid remains same now 5 rho naught by 2. Liquid density rho naught into 4 minus 3h by h naught. 3h by h naught, rho naught get cancelled. So which upon simplification 3h by h naught is equal to 4 minus 5 by 2, 3 by 2. 3 get cancelled, therefore h is equal to h naught by 2. Into h naught by 2. Okay. Now, so the body is in equilibrium at a depth h is equal to h naught by 2 from the surface. At depth h naught by 2 it is in equilibrium where the density of the solid and liquid are equal. Now if we disturb the body from its equilibrium position, it executes oscillations. If we disturb the body from its equilibrium position, it executes oscillations. Now, as we go down, as depth increases, the density of the liquid decreases now. So as we move up, density of the liquid is more solid than solid density. Density of the liquid is more, buoyancy force is acting upward. So if we just push that solid above the equilibrium position by small amount, so that extra buoyancy will be created. Therefore, restoring force can be calculated as extra buoyancy force. Therefore, restoring force is equal to extra buoyancy. Extra buoyancy. Restoring force is equal to extra buoyancy. Now, if we disturb that solid from its equilibrium position by small amount, then extra buoyancy created due to which, where when it is above the equilibrium position or below the equilibrium position, if we can move, below the equilibrium position, if we can move. So extra buoyancy, or it experiences a net force. Net force here, when H is equal to H naught by 2, 3 by 2, 5 rho naught by 2. When we go down further, density of the liquid, what happens? We go down further by small amount, buoyancy force is acting upward and mg is still acting downward. Mg remains constant and extreme buoyancy when it is go down by a distance x is equal to volume is equal to mass by density of the solid into density of the liquid into z. Mass by density of the solid, we get 5 rho naught by 2. Density of the liquid, when it go down from that equilibrium position, so as density of the liquid varies, as rho naught into 1 minus rho naught into 4 minus 3h by h naught. 4 minus h by h naught. From that equilibrium position, we can move the solid by a depth x below it equilibrium position. By 3h by h naught. 3h by h naught, where h value we can write it as h naught by 2 plus x into 3. That is the buoyancy force acting on the solid when it is pushed down by a distance x. Pushed down by a distance x into g. Therefore, that first term will cancel out now. First term will cancel out here because 2m by 5 rho naught. Rho naught get cancelled. 2m by 5.
6 mg by 5 h naught.
2mg by 5, which upon simplification 4 h naught minus h naught by 2 plus x into z plus 3x, not this one. It should be 3x, which upon simplification we get 2 into 4, 8 minus h naught. Here we get h naught term. So 2mg by 5 h naught into 4 h naught minus h naught by 2. 7 h naught by 2 plus 2 into 3, 6x by 2. 2 get cancelled. 2 get cancelled. We get 7 h naught plus 6x by 2 into g. 2 get cancelled. So by comparing with that, we get 7 by 5, h naught get cancelled, mg plus 6 mg x by 5 h naught. 6 mg x by 5 h naught into x. Here minus mg term is there now. This is buoyancy minus mg term here we have. We have to calculate the restoring force as buoyancy force minus mg which upon simplification what we get here 5 mg 2 mg by 5, which here we have 3 h naught by 2 2 4s are 8, 5 h naught by 2. Here we have 5 h naught because we multiply with 3. So 2 into 4, 8 h naught minus 3 h naught by 2. So 5H0 here, 5H0 get cancelled, 2 get cancelled. So here we have Mg term only. Here we have Mg term only. Therefore, Mg term get cancelled. Mg term get cancelled. So we get 6 Mg by 5H0 into X. This is the extra buoyancy actually. This is the extra buoyancy term when it is pushed down by a distance X. Therefore, that restoring force is provided by extra buoyancy. So here we have to compare with this restoring force with the spring force. That is compare with effective spring constant into X. Therefore, effective spring constant for this process, we get it as 6 mg by 5H0. Therefore, time period of oscillation, we get 2 pi root over m by k effective. So 2 pi root over m by k effective by m or m by k effective, we get 5H0 by 6g. 5H0 by 6g. So in case of floating object, if you want to find the time period of oscillation, we need to calculate the extra buoyancy if we displace the body from its equilibrium position. If we displace the body from its equilibrium position, extra buoyancy we need to calculate. So here the block is in equilibrium at a depth h0 by 2 from the surface, where the solid density and liquid density are equal at x equal h0 by 2. Therefore, if we displace the body by small distance x in the downward direction, so due to which that block will experience an extra buoyancy force. So that's why we try to move back. It again try to move back to reach their equilibrium position. Therefore, it executes oscillations about this equilibrium position or mean position. It executes oscillations about the mean position. So given it is, the block will perform SHM and the frequency of oscillation we get 1 by 2 pi into root 6g by 5H0. So here the block will perform SHM because the spring force or restoring force is proportional to displacement, but opposite in direction. And next 7 and 9 and any other 11th one, no?
కాదు సార్ పేపర్ 2 లో కాదు అయిపోయింది.
11th one also we did in superposition of 2 or more SHMs. Tensors తీసుకొని solve చేయాలి. So this week we have entire heat and thermodynamics. Start చేసారు ఏమన్నా కాన్సెప్ట్ హీట్ అండ్ థర్మోడైనమిక్స్? హెవీ ఉంటుంది వీక్ సిలబస్. ఎంటైర్ హీట్ అండ్ థర్మోడైనమిక్స్, ఇట్ ఈస్ నాట్ ఈజీ థింగ్. So in this week's syllabus, total entire heat and thermodynamics. So first of all, basic thing that is conversion of the temperatures, no? Conversion of the temperatures. So what that branch here? Relation between different scales. Yeah, thermometry. Yeah. So first thing we have thermometry. So here we need to know the relation between different scales of temperatures. Relation between different scales of temperature. And next, expansion of solids. Expansion of solids. So we define alpha, beta, gamma, and the variation of that density of the solid with the temperature. and that application related to simple pendulum and application related to elasticity. Okay, in this way, we need to see the expansion of the solids and expansion of liquids. Expansion of liquids. In that expansion of liquids, we define alpha, beta, and gamma for solids. Some application related to the simple pendulum and elasticity and bimetallic strip and rods when they are joined together, expansion of that combined rod and thermal stress and thermal strain and related problems. And also we can see variation of that density of the solid with the temperature. And expansion of solids, we define apparent expansion and real expansion. For that liquids we have, because the liquids cannot be heated directly, So by taking in a solid, we heat the liquid. That's why that expansion of the liquid is of two types. One is the actual expansion of the liquid, that is known as real expansion. Another one is expansion of the liquid with respect to the container. Expansion of the liquid with respect to the container. So that is expansion of liquid. And calorimetry. And heat transfer and expansion of gases, that is KTG. Expansion of gases and KTG, kinetic theory of gases. In KTG only we have to discuss about expansion of gases and thermodynamics. So questions are frequently given. These two are important. And next, expansion of solids and the heat transfer. And these are in order. And further you go to remaining problems. Expansion of liquids, sometimes they may give calorimetry. Calorimetry is important for advance. Okay, heat loss and heat gains and method of mixtures problems. Important for advance. And thermometry sometimes. The most important, KTG and thermodynamics, and further mains and as well as advanced also. So for advanced, we need to check further calorimetry and then go for solids, heat transfer, and liquids and thermometry. This is the order. And basic thing we know that in thermometry, we have to relate we have to convert the temperature in one scale to another scale. See, in any scale, the temperature to be measured should be constant, and which varies linearly with the temperature, according to old thermometry. According to that, in any scale of measurement, reading minus lower fixed point by upper fixed point minus lower fixed point is constant. Where LFP means here to define to calibrate to construct the thermometer, we need to define two fixed points. So that is known as LFP and UFP, upper fixed point and lower fixed point. So general upper fixed point can be taken as boiling point of that substance, thermometric substance, and LFP is taken as melting point of that thermometric substance. Then in Celsius scale, Fahrenheit scale and Kelvin scale, we write C minus. Lower fixed point in Celsius scale, it is 0, and upper fixed point is 100. And in Fahrenheit scale, lower fixed point is 32 degree Fahrenheit and upper fixed point is 212 degree Fahrenheit. And in Kelvin scale, K minus 273.15 by upper fixed point 373.15 minus 273.15. And we have Reamer and Rankine scale. So Reamer and Rankine scale. In Reamer scale, so we have 0 degree Reamer and 80 degree Reamer as the lower and upper fixed points. and the Rankine scale. So usually they are not asked about this Reamer and Rankine scales. So RA Rankine scale, we get RA minus 492 by 672 minus 492. The relation between different scales of temperature, and in unknown thermometer, reading is X, lower fixed point is L, and upper fixed point is U, and the lower fixed point is L. So we have to convert that faulty reading. We have to convert that faulty reading into any correct Celsius reading or Fahrenheit reading by using that equations. So this is faulty or unknown thermometer. Unknown thermometer, unknown scale. So in which X indicates the reading in that unknown scale, and L indicates the lower fixed point, and the U indicates the upper fixed point. U indicates upper fixed point. Therefore, and this is a Celsius scale, and this is Fahrenheit scale, and this is Kelvin, and this is Reamer, and this is Rankine. Reamer and Rankine scale. So like that in different scales. So we have to relate that temperatures like this to convert that one temperature in one scale to another scale. And if we consider generally, they give Celsius, Fahrenheit, and Kelvin scale. If we talk about Celsius, Fahrenheit, and Kelvin scale, we write directly it as C by 5 is equal to F minus 32 by 9 is equal to K minus 273.15 by 5. Only while relating these three, generally we use this relation C by 5 equal to F minus 32 by 9, that is equal to K minus 273.15 by 5. Here, in Celsius scale and Kelvin scale, so to convert that Celsius reading into Kelvin, we have to add 273.15, 273.15. And if suppose in temperature difference, if we can take, so in temperature difference, in these scales, generally related as delta C by 5 is equal to delta C by 5 is equal to delta F by 9 is equal to delta K by 5. From this, we conclude that 1 degree Celsius rise in Celsius scale, 1 degree rise in that temperature in Celsius scale is equal to 1 Kelvin rise. Means 30 degrees Celsius minus 20 degrees Celsius, that we get 10 degrees Celsius. And 30 Kelvin minus 20 Kelvin also we get 10 Kelvin. Means the temperature difference in Celsius scale and Kelvin scale are equal. Temperature difference in Celsius scale and Kelvin scale are equal. Means if we convert this 30 degrees Celsius into Kelvin scale and 20 degrees Celsius into Kelvin scale, and again if we can find the temperature difference, you get again 10, the difference in temperatures. Means difference in temperature in Celsius and Kelvin scale is same, but readings are not same. Temperature differences are equal. Means 1 degree Celsius increment in Celsius scale is equal to 1 degree increment in temperature in Kelvin scale. That increment in temperature is same in Celsius and Kelvin scale. So, but increment in temperature in Fahrenheit and Celsius scale is not same. So 1 degree Celsius increment is equal to 9 by 5 times the Fahrenheit scale. 9 by 5 times the Fahrenheit scale. Therefore, so if you want to convert that temperature difference in Celsius scale, 1 degree Celsius difference scale is equal to 1.8 degree Fahrenheit interval. 1.8 degree Fahrenheit interval. 1 degree Celsius interval is equal to 1.8 degree Fahrenheit interval. 1.8 degree Fahrenheit interval. Means we need to multiply to calculate the temperature difference in Fahrenheit scale. If temperature difference in Celsius scale is given, we need to multiply with 1.8. But to convert 1 degree Celsius into Fahrenheit, that is different. But here 1 degree Celsius interval is, if we want to convert, means 10 degrees Celsius interval. 10 degrees Celsius interval. So for example, the difference in temperature between 30 degrees Celsius minus 20 degrees Celsius. So if you want to convert this change in temperature in Celsius scale is 10 degrees Celsius. If you want to convert into Fahrenheit, so 10 by 5 is equal to delta F by 9. Therefore, delta F we get it as 18 degree Fahrenheit. Means 10 degrees Celsius difference in Celsius scale is corresponding to 18 degree Fahrenheit. And 10 degrees Celsius increment in Celsius scale is equal to 10 Kelvin interval. 10 Kelvin interval. So that is the difference. Now, if you see the graph between Celsius and Fahrenheit scales are given, C is equal to 5 by 9 into F minus 32. So we get it as 5F by 9 minus 160 by 9 is the Celsius reading. 5F by 9 minus 160 by 9. By taking Celsius on y-axis and Fahrenheit on x-axis, if you draw the graph, so this graph is in y is equal mx minus c form. Y is equal mx minus c form. Here we have negative y-intercept on Celsius scale and a positive slope. So the graph will be like this. It will intersect the negative y-axis at minus 160 by 9 and slope of the graph. When f is equal to 0, when c is equal to 0, f is equal to, we get 32 degree Fahrenheit. 32 degree Fahrenheit and slope of the graph. Slope of graph between, by taking Celsius on axis and slope of 5 as 5 by 9, from that they may give sin theta or cos theta value if the graph is drawn between Celsius versus Fahrenheit. If suppose, if by taking that Fahrenheit on y-axis and Celsius on x-axis, F minus 32 is equal to 9c by 5, because c by 5 is equal to F minus 32 by 9, F is equal to 9c by 5 plus 32. That is in the form of y is equal to mx plus c. So here positive y-intercept we have. Positive y-intercept and the slope of the graph. Slope of the graph we get tan theta, that is equal to slope of graph drawn between Fahrenheit on y-axis and Celsius is taken on x-axis. So slope we get it as 9 by 5. Slope we get 9 by 5. So that is the slope of Fahrenheit versus Kelvin, Celsius. If we draw the graph between Celsius versus Kelvin, we get a straight line crossing through origin. Sorry, not origin. So for the slope of the graph, we get Celsius versus Kelvin. If we draw the graph, by taking Celsius on x-axis and Kelvin on y-axis, K is equal to C plus 273.15. Then slope of the graph, we get it as 45 degrees. Well, y is equal to m value here 1. So here slope of the graph, we get 45 degrees. This intercept when c is equal to 0, k value becomes 273.15. And when k is equal to 0, this value we get minus 273.15 degrees Celsius. Means minus 273.15 degrees Celsius is equal to 0 Kelvin. The temperature is known as absolute zero. Minus 273.15 degrees Celsius is known as absolute zero. That is 0 Kelvin. 0 Kelvin. So that is in thermometry. Generally, we need to convert one units in one temperature in one scale to another scale. You can see explanation of the solids. And one more here, based on the thermometric property, that scales are constructed. Based on the thermometric property, scales are constructed. This is depends on calibration of scale. Depends on calibration of the scale, that different scales we have to construct, and depends on the thermometric property, which varies with the temperature. So based on the thermometric property, which varies with the temperature, so according to old thermometry, we can construct that thermometric substance which varies with the temperature. Yes, if X is some thermometric substance which varies with the temperature linearly, yes, AT plus B, according to old thermometry. Old thermometry, where X is thermometric substance. Thermometric substance means like resistance of wire, or pressure or volume of gas, etc. Or liquid is taken in a considered as a thermometric substance. Like that, according to old thermometry, that thermometric substance which varies with the temperature according to that equation. Now, if X0 is a thermometric substance at 0 degrees Celsius, X0 is the thermometric substance. So A into 0 plus B, and at 100 degrees Celsius, thermometric substance is X100. So we write A into 100 plus B, and at T degrees Celsius, we use XT, that is A into T plus B. So by solving that set of that equation, the temperature to be measured can be calculated as XT minus X0 by X100 minus X0 into 100. By solving, we get, so the temperature to be measured in degrees Celsius. The temperature to be measured in degrees Celsius can be calculated as XT minus X0 by X100 minus X0. Means if suppose in resistance thermometer, they give resistance values at 0 degrees Celsius, at 100 degrees Celsius, and at T degrees Celsius. then temperature to be measured can be calculated as RT minus R0 by R100 minus R0 into 100 degrees Celsius. RT minus R0 by R100 minus R0 into 100 degrees Celsius. Like in gas thermometers, at constant volume gas thermometer, they give pressure at T degrees Celsius, pressure at 0 degrees Celsius, pressure at 100 degrees Celsius in minus P0 into 100 degrees Celsius. Or in constant pressure gas thermometer, volume at T degree they give, and volume at 0 and volume at 100 they give. From that we need to calculate the temperature to be measured. The temperature to be measured in gas thermometers. So like this we can calculate in different thermometers, gas and as well as resistance thermometer, like that. And according to modern thermometry, instead of two fixed points, 0 and 100 degrees Celsius, so we use Kelvin temperature. Kelvin temperature means we have to define that at a triple point. We have to define the triple point of water as taken as a reference point. So with respect to that, we have to define that temperature to be measured can be calculated. Temperature to be measured can be calculated. Therefore, at a triple point temperature, thermometric substance is X 273.15 at a triple point. At the triple point temperature, X 273.15 is equal to A into 273.15 Kelvin. Therefore, the temperature to be measured in the Kelvin scale, here it is in degrees Celsius and in Kelvin scale. So we have to measure the temperature as XT. We can say this is XT at temperature T by X 273.15 into 273.15. So in the problem they give thermometric property or resistance of the wire. Resistance of the wire at some temperature they give, and at resistance of the wire at a triple point temperature they give. At a triple point temperature they give. Therefore, the pressure of the gas at a triple point temperature they give. At some other temperature we need to calculate the at what temperature pressure becomes 2 times of that pressure at a triple point temperature, like that they give. Suppose pressure of the gas is given as some 2.5 times the pressure at a triple point. Pressure at triple point temperature. Triple point temperature means we rate it as 273.15 Kelvin is the triple point temperature or PTR. So pressure of the gas at some temperature is given as 2.5 times the pressure at a triple point. Then what is the temperature of the gas? Temperature of the gas. Now here we can substitute here, that is 2.5 times the pressure at 273.15. So that temperature of the gas should be equal to 2.5 times the 273.15 Kelvin. 273.15 Kelvin. So like that we have to calculate the pressure or volume of the gas at a triple point is given. So that is about thermometry. Now tomorrow we can see expansion of the solids. Expansion of solids. And you can go through that. Generally you have an idea about that Cartesian thermodynamics. Okay. So parallelly you can check that problems from that Cartesian thermodynamics. Okay. From back you can come. So we'll go from starting from expansion of solids, liquids. Okay. And I will send an assignment. Tomorrow I will send an assignment. Concept we have in this week. And once again recheck that concept. Okay.
Okay, sir.
Then you start doing the problems from tomorrow onwards. Today you need to finish the concept on entire week maximum and prepare some short notes while reading. That will be useful for that final exam or for final preparation. ఓకే, వస్తున్నారా ట్యూస్డే వెన్స్డే నుంచి కెంపస్ కి?
Wednesday.
Wednesday onwards. Okay, note these points and take a snapshot if you require.